This is the first question. I know this question's a little bit old, so you probably won't see, or we've already done this question before. I think I gave it to you guys during one of the exams. So let's look at it again, just so we see what we're going to do. So here we have first response questions from 1982. This is a very old first response question, but this is all kinematics, right? So here we have the first meters of a 100-meter dash are covered in 2 seconds by a sprinter who starts from rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity as the sprinter had after 2 seconds. So part A is asking to determine the sprinter's constant acceleration during the first 2 seconds. Okay. So what we know here is that hold up, sorry guys. Okay. So what we know here is that during the first 2 seconds, the sprinter is accelerating, right? So remember in kinematics, we have several equations for kinematics. The first equation is going to be this. Oops, sorry. I don't know why it's dragging. Yeah, velocity is equal to distance over time, right? So this is the first equations that we have. So this is the first equation that we have. Velocity equals distance over time. This is the basic like velocity equation, right? So this equation, what it is when we're looking at objects that are moving with no acceleration. So we only utilize this equation if there is no acceleration, right? If the acceleration is 0, then we will use velocity is equal to distance over time, right? But if there is acceleration, then we can use our other equations. Remember, Vf is equal to Vo plus At. Then we have change of x is equal to Vot plus 1/2 At squared. And then finally, we have Vf squared is equal to Vo squared plus 2a change of x. So these are all the kinematics equation. We use these 3 equations if there is acceleration, right? So what we know based on this equation again, or this question, is that the first 2 seconds of the 100-meter dash, the sprinter has a constant acceleration. Okay, so the sprinter is moving and is speeding up at a constant rate for the first 2 seconds. Then after the 2 seconds, he runs with he's going to run with the same velocity he has. So after the 2 seconds, he's going to be running with a constant velocity, meaning 0 acceleration. Okay. So here that we have, so what we're going to look for is the constant acceleration during the first 2 seconds, right? So we know that there's going to be acceleration, so we know we're not going to use this equation. We know we're going to use one of these 3 equations because we know in the first 2 seconds there is acceleration. Okay, so let's look at so we know during the first 2 seconds, right? So we know like the first 2 seconds, the time, right? So we're just going to look for the first 2 seconds, right? So we know several things about the first 2 seconds, right? We know that it's 100 overall, it's a 100-meter dash, right? And then 90 meters, right, is ran with the same velocity. 90 meters is after the 2 seconds, right? So that's very important to understand. 90 meters is after the 2 seconds. So that means in the first 2 seconds, right, the change of x or the displacement is only 10 meters. Okay, so that's very important to understand. During the first 2 seconds, the displacement during the first 2 seconds is 10 meters. That means the runner ran 10 meters in the first 2 seconds. Okay. We also know, right, and this is very important. We also know, right, because of this starts from rest, that the starting velocity is 0. Right. So remember what I told you guys with any kinematics, right? With any like questions about kinematics, as long as you know 3 of the things, you know everything. Right? So I know time, I know change of x, and I know VO. Which of the 3 kinematics equation can I use to find the acceleration during the first 2 seconds? Right? Please type in your answers on chat. So which equation can we use to answer part A? Okay, so the second equation, right? So we know change of x is 10. Let's try this out. We know VO is 0, right? We know time is 2, but that's irrelevant, right? Plus 1/2 a, and then I know time is 2 seconds. Okay. All right, sounds good, guys. Okay, so we can obviously solve for this, right? Like, this is a pretty easy like calculation. 10 is equal to 0 times 2 is just 0. 1/2 a, and then what 2 squared is 4, right? So 1/2 times 4 is 2a, and then you find out that a is equal to 5, right? And that's going to be 5 meters per second squared. And that's it, right? So we figured out the first part of the problem. The first 2 seconds, the runner was moving at an acceleration of 5 meters per second squared, right? And that's it. That should be pretty simple. Okay, so that we know, right? So now let's figure out like what's going on with the rest of the time, right? So part B is saying during the sprinter's determine the sprinter's velocity after 2 seconds have elapsed, right? So what are we looking for there? Okay, what are we looking for part B? Determine the sprinter's velocity after 2 seconds have elapsed, right? So what are we looking for there? Again, if you have an answer, just type it in the chat. Again, for part B, I want to know, determine the sprinter's velocity after 2 seconds have elapsed. What are we looking for there? It's fine if you're wrong. We haven't touched kinematics in months, so. A change in what, though? Right? So we know. So, like, obviously, like, if you look at this, right? Determine the sprinter's velocity after 2 seconds. Right? It is a velocity, yes. But, like, what velocity are we going to find? Right? At least for the first 2 seconds. We know that we started off with, like, from rest, so we started off with 0 velocity. Yeah, you're a good idea, VF. So we're looking for the final velocity during the first 2 seconds. Not the entirety of the 10 or not the entirety of the 100-meter dash. It's just going to be the first 2 seconds of the 100-meter dash. So we're going to look for the final velocity, knowing that this guy, right, that this runner is starting from rest. We can find the final velocity at 2 seconds, right? So which equation can I find there? The first equation, yeah, because we know the acceleration now. So we can use VF is equal to VO, which is 0, plus acceleration times time, right? So we know the final velocity will be 10 meters per second. Okay? Again, that should be pretty simple. Oops, sorry. So we know, right? So we know a lot of things about the first 2 seconds. First 2 seconds, we know, started from rest, ended at 10 meters per second. It had an acceleration of 5 meters per second squared, and it was a 10-meter displacement, right? So we know everything about the first 2 seconds. Now we're probably going to figure out about, like, the rest, right? So part C is saying, determine the total time needed to run the full 100 meters. Right, so we know the time it took to run the 90. So we know the time it took to run the 10 meters, right? So the first 10 meters of the race took 2 seconds, right? So we're going to look for the rest of the time, the 90 meters. How long did that take, right? So we know, based on the problem, that for the remaining 90 meters after the first 2 seconds, the runner was running with a constant velocity, meaning an unchanging velocity. The velocity is going to change to stay the same. Sorry. So whatever final velocity it had at 10 meters per second is going to be the constant velocity this runner is going to have for the rest of the 90 meters, right? For the rest of the race. Since we know that, and since we know for those 90 meters, there's no acceleration or there's a constant velocity, which equation are we going to use? So again, right, I want to find the time it takes for the entirety of the 100 meters. I already know the time it takes for the first 10 meters. I just want to find the time it takes for the rest of the 90 meters, right? But the 90 meters is being ran at a constant velocity, which means no acceleration, right? So which equation are we going to use to find the time it would take to run that 90 meters? What do you mean by 1? Like the first kinematics equation, like the VF is equal to VO plus AT. So okay, so none of those are correct. Let's see what. Oh my gosh, nope. So if the first, second, and third equations. All right, so okay, so Danny's right? It's going to be v is equal to distance over time. We're going to use this equation for the purposes that there is no acceleration. So remember, in the 90 meters, there is no acceleration, meaning we're going to utilize this equation. We know the velocity during the 90 meters. It's going to be the velocity that the runner had after the 2 seconds. So we know for the rest of the race, the runner is going to run at the velocity of 10 meters per second. Since I know that, I can just plug it in. I know the distance will be 90 meters, right? And how much time will that take, right? If you do the math, it would be time is equal to 9 seconds, right? So we know during the last 90 meters, it will take the runner 9 seconds to run. Any questions? Unless I did my math wrong. Yeah, it is. If you plug in 0, that works too. Yep. So we know the time is going to be 9 seconds. So we know overall, how long does it take for this runner to run 100 meters? $11 seconds. Good. Right? So it's going to be 11 seconds. And we know that just because, right? So the last part, because we know that because the first, the first 10 meter was ran in 2 seconds, and then the rest of the 90 meters was ran in 9 seconds, right? So 9 plus 2 is 11. It's pretty simple stuff. So let's look at part D. So part D is on the axis provided below, draw the displacement versus time curve for the sprinter. So we're going to have to draw the graph, and we're going to have to utilize like displacement and time. Displacement is our y-axis, time is our x-axis, and graph our information, right? So in the beginning, right? We're obviously going to be at 0 displacement. Okay, so that's very important to understand. In the beginning, we're obviously going to be at 0 displacement. Okay, and then obviously we're going to go up. Right? So this is very important. Obviously, we're going to go up, and in the first 2 seconds, how many meters did we run, or did this person run? $10 meters, right? So we know from 0 to 2, you're going to start at 0, right? From at time 0 or 0 seconds, we're at the starting point, which is 0 displacement, right? And then we're going to go up to 10 meters, right? We're going to go up to 10 meters during the first 2 seconds. But remember, this is very important. The first 2 seconds had an acceleration. So how will our line look like in a displacement versus time graph, right? Will it be a straight line? Will it be like a curved line? Like, how will our line look like from 0 to 2 seconds? Since there is an acceleration. Increasing, yeah, but it would be like a straight increasing line, right? It will be a linear increasing. Will it be like a curved? Yeah, so it would be a curve going up because there is acceleration. Because remember, acceleration means like there's a change in velocity. So if they're in a displacement versus time graph, if there's an acceleration, our graph would be like a bit curved, right? So our graph will kind of look like this. Not exactly this because I can't draw, but it would look exactly this, right? So for the rest of the time, and this is very important, right? It takes us 11 seconds to get to 100 meters. So that's very important. That's what we know. At 11 seconds right here, we're going to be at 100 meters. So now, during 2 to 11 seconds, we know there is no acceleration, meaning constant velocity. So how will our line look like from 2 to 11 seconds? It's going to be a linear line going up, right? Again, I can't draw, and I don't have a straight edge, so I'm just going to try to draw a straight line. So that should be a straight line, like a linear line going from 2 to 11 seconds, and that's it. And this problem is done, right? Again, this should be pretty simple. Okay, any questions about this problem? Okay, so let's move on. We're not going to do the 2006 question. I think I like the 1993 question. So let's look at 1993. Okay, so here, this is a question from 1993 from an AP exam. So here we have a student that's standing in an elevator and records his acceleration as a function of time. So you're going to see in kinematic questions, it's going to be a lot of graphs, right? Yeah, so there's going to be a lot of graphs when it comes to like kinematics and stuff like that, right? So the data is shown in the graph above. At time t is equal to 0, the elevator is at a displacement of x is equal to 0, and the velocity of v is equal to 0, meaning at time equals to 0, or at 0 seconds, we're starting from rest, right? Assume that the positive direction for the displacement, velocity, and acceleration are upward. We're in an elevator, right? So we're going to treat this direction as positive. So let's look at, let's analyze the graph that's in front of us, right? The graph that's above. So the graph above is the acceleration versus time graph, okay? So instead of looking at velocity, instead of looking at displacement, we're looking at an acceleration as our y-axis, okay? So we know the acceleration during the first 5 seconds. We know the acceleration from 5 to 10 seconds, and so on and so forth, right? So the acceleration from 0 to 5 seconds is 0, meaning there is no acceleration during that time, meaning there's like a constant velocity during that time, right? From 5 to 10 seconds, we know the acceleration will be 4 meters per second squared, which means like during that time, the acceleration or this velocity is changing or increasing by 4, right, each second. And then 10 to 15, we're back to 0, and then from 15 to 20, we're at negative 4 meters per second squared, right? So during that time, there's going to be a negative 4 meters per second squared acceleration. Okay, so let's look at part A. Determine the velocity v of the elevator at the end of each 5-second interval. Okay, so this is very important, guys, right? So what we're going to look for here is we're going to look for the velocity, right, of the elevator at the end of the 5-second interval. So we're looking at it at 5 seconds. We're looking at it at the velocity at 10 seconds, then at 15 seconds, then at 20 seconds, right? So we're looking for the velocity, right, at the end of each of these intervals, okay? So 0 to 5 is going to be the easiest one, right? From 0 to 5 seconds, we know the acceleration based on this graph is 0 meters per second squared. So I know the acceleration is 0, meaning that we're going to have a constant velocity, right? We also know something else. We know that the velocity, right, the velocity at 0 seconds, our starting velocity, is going to be 0, right? That's based on this. Our starting velocity is going to be 0. We also know, right, our x during that time is 0, but that's kind of irrelevant, right? So we know that during the first 5 seconds, let's make t is equal to 5, right? What equation can I find or can I use to find the velocity at the end of the 5 seconds, right? What equation can I use? Or what can I do to figure out? I can use the first equation. Yeah, I could use that, right? So I can do VF is equal to VO plus AT. So I know VF, I know VO is 0, I know acceleration is 0, and I know time is 5, right? So overall, we figured out that the final velocity at the end of the first 5 seconds is 0. Okay? So right here, 0 meters per second. Okay? That's the easiest one, right? So now let's look at from 5 to 10 seconds. So now, from 5 to 10 seconds is going to be a little bit different because now there is an acceleration. We know the acceleration is positive 4 meters per second squared, right? So let's look at what we know during this time. I know the acceleration is 4 meters per second squared, right? I know the time will still be 5 because from 5 to 10 seconds is 5 seconds. The change of time, it will be 5 seconds, right? And I know, and this is very important, and I know the starting velocity, and then we're looking at this interval now. We're looking at the interval from 5 to 10 seconds. The starting velocity at 5 seconds, right, is 0, right? Because we know during the first 5 seconds, there was no velocity, right? The object didn't move the entire time. So we know the starting velocity will still be 0 meters per second. And we can still use the first equation, right? So we have VF is equal to VO plus AT. VF is equal to 0 plus A, which is 4, times T, which is 5. And this will be 20 meters per second. So we know for the next interval at 10 seconds, right? The final velocity at 10 seconds will be 20 meters per second. Okay. So now, and this should be pretty simple, right? For the third interval at 15 seconds, I want you guys to find what the speed would be. What would be the speed of this elevator at 15 seconds? And type in your answer once you figure it out. Yeah, it would be 20 meters per second, right? And this is very important, right? So during the 10 to 15 seconds, there was 0 acceleration. If there's no acceleration from 10 to 15 seconds, it means that the velocity will not change. So whatever velocity it had at 10 seconds, it will have at 15 seconds because there is no acceleration, which means there is no change in velocity. So the velocity will still stay the same. Okay, so that's 10 to 15. So now let's look at 20, right? So again, we know a lot of things. We know the acceleration from 15 to 20, that interval will be negative 4 meters per second squared. We know the time will still be 5 seconds because each interval is 5 seconds long. And we know that the starting velocity, and this is very important, at 15 seconds, right, is going to be 20. So we can utilize our equation, VF is equal to VO plus AT, which is going to be 20 plus negative 4. And this is very important that you guys put the negative here. Negative 4 times 5, and we find what? And we find... I don't think so. VF should be... right, it should be 20 minus 20, and VF should be 0 meters per second. right? And this is very important that you to understand that, right? So if you look from 5 to 10 seconds, the change in velocity during this time is 4 meters per second squared. In the same interval of time, from 15 to 20, the change in velocity is negative 4 meters per second squared, with the same amount of time, the same amount of time interval. So we know that they probably would cancel each other out. And that's why we get back to 0 meters per second at the end. Okay, so let's look at what else? What did they want us to do? They want us to indicate the results by completing the table, right? So this should be pretty simple. From 0 to 5, right? There was no change in velocity. It was just a straight line like that. From 5 to 10 seconds, we went to 20 meters per second. Now, how will my graph look like? Right? So now this is a velocity versus time graph, right? How will my line look like from 5 to 10 seconds, right? What kind of line will I be drawing here? Yes, it's going to be a linear line, right? That's it, right? Because there's a constant acceleration, right? The acceleration is constant during 5 to 10 seconds, right? It's constant because it's a straight line. The acceleration doesn't change during the 5 to 10 seconds. So we're going to have a straight velocity versus time graph, right? So back to 10 to 15, right? There is no acceleration. So how will my graph look like, right? If there is no acceleration from 10 to 15, how will my line look like, right? How will I draw my line? Or where will my line be drawn? Yeah, kind of, right? Kind of, right? It will be a straight line, but how will it's going to look a little bit different. It's going to be constant, right? So there is no acceleration during 10 to 15, which means there's no change in velocity, which means our velocity is just going to be a line, right? And then finally, this is going to be like this. Okay, and that's it. That's how my graph looks like. Again, this should be pretty simple. Okay. So next is determine the displacement of the elevator. So I'm looking at this part. Determine the displacement x of the elevator above the starting point at the end of each 5-second interval. Indicate the result by completing the following table: 0 to 5, 5 to 10, and so on and so forth, right? So instead of looking at the for the velocity during this time intervals, we're looking for the displacement during this time intervals, right? And this problem can easily be solved using our kinematics equation, right? Since we know a lot based on what we did up top, we know a lot about like the each of the intervals, right? So I can easily solve this utilizing, right, our kinematic stuff, right? But let's just look at it like conceptually, right? To do this as easily and as fast as possible, let's look at this conceptually. So if I look at like from 0 to 5 seconds, we know that there is no velocity, right? That this object didn't move from 0 to 5 seconds. So what displacement should it have during that time? Yeah, exactly, 0. It didn't move, man. Like if it didn't move, it had no displacement, right? It had 0 velocity this entire time. It had no displacement. Okay, so now we can utilize from 5 to 10 seconds. So 5 to 10 seconds is pretty simple. 5 to 10 seconds, we know that the velocity, all right, our starting velocity will be 0. Our final velocity will be 20. So we know that, right? So VO is 0, VF is 20. And we know based on over here, over the top graph, we know that the acceleration will be positive 4 meters per second squared, right? And we even know the time. We know time is 5. So we know a lot of things, right? We know a bunch of things about this problem. So I can utilize pretty much every single one of my kinematics equation to figure out the change in x or displacement. Okay, so let's utilize what's be the nice one to utilize here. I can utilize the second equation, right? So we're going to utilize change of x is equal to VOT plus 1/2 AT squared. Okay, so let's look at this equation. We know VO is going to be 0. We know time is 4, but that does, or sorry, time is 5, but that doesn't really matter because 0 times 5 is 0 anyways. Plus 1 half AT squared. Ooh, sorry. Plus 1 half. Acceleration is 4. Time is 5 squared. Okay, and we're going to get like 5 times 5 is 25, times 4 is 100, divided by 2 is change of x will be 50. So the change of x during 5 to 10 seconds will be 50 meters. Okay, that's it. That should be pretty simple. How about then, like, from 10 to 15 seconds? Right? From 10 to 15 seconds, we know there was no change in acceleration, right? We know that there's going to be constant velocity, so we should automatically know that we're going to use this equation. V is equal to distance over time. I know the velocity during this whole time, it's not going to change from 10 to 15 seconds. Yes, you can just find the area under the curve. Right, so it'll be 20 is equal to distance over this 5 seconds, and you find out 20 times 5, which is going to be 100. So this is going to be 100 meters. But Paulina's right? Instead of doing the kinematics equation, what you guys should already know is that in a velocity versus time graph, to find displacement, all you have to do is find the area under the curve. Right, so if I wanted to look for the area between 5 to 10 seconds, I would find the area of this triangle, right? If I know like the width is 5, the length is 20, 20 times 5 is 100, but it's a triangle, so divide by 2, so this will be 50. We know that this is going to be a rectangle with a width of 5 and a length of 20. 5 times 20 is going to be 100. And then same thing for the last part. Width is 5, length is 20. 5 times 20 is 100, divided by 2 is 50. Right? So those should, right, and she's right. Though we could have done that instead. We can find the area under the curve instead. So again, it's important to understand that like there are shortcuts that we can do, but you have to know them, right? You have to know these shortcuts because they make things a lot easier. So if you find the area under the curve, you can easily find your answer. So overall, if I wanted to find like the displacement during this entire time, I would just have to add up these numbers. 50 plus 100 plus 50, which is going to be 200 meters. Okay. So part two of part B is saying plot the displacement as a function of time on the following graph. Okay. So we know from 0 to 5 seconds, there was, again, 0 displacement. My line looks like this. We know at 10 seconds, we'll be at 50 meters. Okay. And we know at 15, we're going to go up another 100. So this is very important. We're not going to go from 50 to 100. We know that we're going to, remember, displacement is change of x. So that would be like the change in position. Right? So the change in position is 100. So we're going from 50, then we're going to add 100. So we're going to be at 150. Okay. And similarly, from 15 to 20, right, the displacement will be positive 50. So we're going to go up another 50 meters. Right? So, but my question is, and this is very important, right now that we have a displacement versus time graph, how will my line look like at each of these intervals? How will my lines look like at each of this interval? No, right? Not exactly. For one part, yes, but not for each interval, right? Each interval is different because in each interval, right, if you look at here, there's acceleration at 5 to 10, no acceleration at 10 to 15, but there is a negative acceleration at 10 to 20. Right, so our graphs will look a little bit different at each of these intervals, right? So how will these look like? Okay, yeah, and yeah, it's going to be a curve, right? So it's going to be a curve that looks like this, right? Because we know it's going to speed up. And then from 10 to 15, because we know there's no acceleration and there's constant velocity, that's when we're going to have a linear line, okay? But this is important. From 15 to 20 seconds, how will that line look like? I guess I don't know what you mean by that. Like curve going down. Okay, I think I know where that's going, right? So the graph will look like this, right? So there's a very important, the reason why it's going to curve this way during 15 to 20 is because we know that it's going to have a negative acceleration, which means that it's slowing down. If it's slowing down, right, the curve will also slow down. Right, it's going to start off kind of fast, and then the slope will steadily decrease and decrease, because the slope indicates speed or velocity in a displacement versus time graph. We know that this the velocity is going to go down, which means the slope of the line will also decrease as we go through time, I guess. So our graph will look like this. Again, pretty simple, right? And that's one. Okay, so I think this is, yeah. So let's try to do this one. This one's from 1994. These are like really, really old. So, and we've seen the questions like this before. So here we have a ball of mass half a kilogram, initially at rest, is kicked directly toward the fence from point 32 meters away, as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees above the horizontal. The top of the fence is 25 meters high. The ball hits nothing while in flight, and air resistance is negligible. So the question, the first part is asking, determine the time it takes for the ball to reach the plane of the fence. So this is like a classic kinematics equation. We've done several of this before. And in these kinds of things, we need to be knowledgeable about vectors, right? We need to look at vectors, and we need to be very knowledgeable about vectors. So the vector that we're given is that we're given at initially, the ball is kicked, right? The ball is kicked at an angle at 20 meters per second. So that's the vector that we have. 20 meters per second with an angle of like 37 degrees, right? So, and this is very important, if you remember when we dealt with kinematics, what did we do first with vectors in an angle? Right? What's the first thing that we do with vectors in an angle? Find its components. Good. We're going to have to find Good. So we're going to have to find the vertical and the horizontal component of this vector, right? So let's find the vertical and let's find the horizontal. Luckily for us, we already know what to do, right? So vertical is going to be sine, horizontal will be cosine, right? So we know it's going to be 20 sine of 37 and then 20 cosine of 37. Make sure your calculator is in degrees, but that's how we would do it, right? What we could have... luckily for us also, if we, especially if we don't have like calculators, yeah, they give us what sine and cosine is. Yeah. So instead of saying 20 times sine of 37, what we can do instead is 20 times 0.6, and then 20 times cosine of 37 is 20 times 0.8, right? Again, should be simple. So we know, and this is very important, so we know that this is going to be our actual velocity. This 20 meters right here is going to be our actual velocity, right? But instead of looking at, like, the reason why we split them up into components is we're going to do this problem twice, right? Or we're going to look at, split this problem up into two different problems. We're going to look at the vertical part, and we're going to look at the horizontal part. So let's split this up right here. So the top will be vertical, the bottom would be the horizontal part. Okay? So let's look at that. So we know vertically, right? If we do 20 times 0.6, that we're going to get 12, I believe, right? So this 12 right here is going to be the vertical velocity, right? So the vertical velocity, or the vertical initial velocity, right? The vertical initial velocity is going to be 12 meters per second. Whereas the horizontal velocity, 20 times 0.8, which is 16, right, is going to be our horizontal velocity. Okay, so that's what we figured out here. By splitting up our 20 meters per second, our actual velocity, we split it up into the vertical velocity. So this is how fast it's going to go initially, right, at vertically going up, and this is how fast it's going to go horizontally, 16 meters per second. Okay, so the actual velocity is 20 meters per second, right? But we have to split it up into its vertical and horizontal, and they're going to be completely different things. Okay, so let's think about like what we know about both the vertical and the horizontal. What do we know about the vertical velocity? Or sorry, what do we know about the vertical component or the vertical motion of the ball? Right, just the up and down motion of the ball. What do we know? We know it goes up, yeah. We also know something. We know something like very important. Not like vertically, not exactly. Yes, we know it goes up and down, but what else do we know about its motion, right? There's something that we know fundamentally. We know its acceleration. We know that up and down, there's going to be an acceleration because we know up and down, it's on. Good. It's going to be at the hands, right? It's going to be at the hands of gravity, right? So we know since the vertical motion, since going up and down, and we know, like we can assume we're on Earth, we know that we're going to have gravity, right, affecting or accelerating this object. Okay, so we know that there's going to be an acceleration here, right? Since it's going up and down, and we know that acceleration is going to be not 9.8, negative 9.8 meters per second squared. And that's going to be the acceleration of the ball due to gravity, right? Because we know gravity affects things vertically, right? It affects the motion of objects when it's going up and down. Okay? So horizontally, do we know that? Good. So horizontally, right, we know that gravity, again, this is very important. Horizontally, we know that like gravity is not affected, right? So there's a reason why I just put VH over here instead of VOH, because we know horizontally, since there's no gravity, and since we can like ignore air resistance and stuff, we know there's not going to be any acceleration in its horizontal motion, right? So there's going to be zero acceleration in its horizontal motion, meaning it's going to have a constant velocity, meaning this velocity right here at 16 meters per second will not change. Okay? That's pretty simple, right? We know that so far. So we know vertically, acceleration is important. Horizontally, there's no acceleration. Okay? So let's look at part A. Determine the time it takes for the ball to reach the plane of the fence. So we want to find when the ball reaches at this position. Okay. So, and this is very important. What can I do to figure that out? How do I find, right? And this is very important. How do I find the time it takes for the ball to go from here, right, to the top of the fence? Okay. Which one should I look at? Vertical or horizontal motion? Yeah. So we could use horizontal motion. We probably should use horizontal motion, right? So we know a lot about it horizontally. We know horizontally, right? The by the time the ball reaches the fence, horizontally the ball, and this is for only horizontally, right? So I'm gonna put change of x horizontally. We know that this object is going to travel 32 meters. So according to this, right? Horizontally, the object is going to travel 32 meters. I can easily find time since I know there's no acceleration using velocity is equal to distance over time, right? So we just do 32 divided by 16, which gives us 2 seconds. Okay, so I know that. So I know this will take 2 seconds. Okay. So actually, since we're running out of time, we're going to end the stream there. Right. Again, if you have any questions, guys, please don't hesitate to ask. whether on Discord or on Google Classroom. Okay, but we're ending the stream there. Thank you guys for showing up. Bye.